Welcome back. In this session we will look into how to solve multi-objective optimization problem using the inbuilt functions of MATLAB. So, MATLAB has these two functions GA multi OBJ and Pareto search, right. So, GA multi OBJ is based on genetic algorithm, whereas this Pareto search is based on pattern search, right. So, both of these functions can solve multi-objective constrained optimization problems, but neither of these functions support integer variables, right. So, problems which do not have integer variables and are multi-objective in nature can be solved by GA multi OBJ or Pareto search. So, here the objective function can be linear or non-linear, the constraints can be linear or non-linear. Though the title of this course is single objective optimization, we are just demonstrating how to solve multi-objective optimization problem. We are not looking into the theory of it, but should you have any multi-objective optimization, you can use one of these inbuilt functions to solve it, right. So, just to help you recollect what is multi-objective optimization, in this we have more than one objective, let us say f1 and f2, right. So, both of these functions are conflicting in nature. So, let us say if we want to improve f1, the solutions have a poor value of f2, but if we improve on f2, the solutions have poor values on f1, right. So, if you remember, we have seen an example in the introduction lecture, you can refer back to it, right. So, here what we are interested is in the set of non-dominated points or the Pareto points, right. So, if both the objectives are to be minimized f1 and f2, remember this is not the decision variable space, this is now the objective function space. Let us say we have these 3 points. So, if you analyze, none of these 3 points are inferior to one another. So, for example, let us say this is point A, this is point B and this is point C. So, point A has a very good f2 value because we are minimizing both the objectives, it has a very good f2 value, but it has a poor f1. Similarly, B, if you see, it has a f2 which is poor to A, right, but it has an f1 which is better than A. Similarly, FC, if we see, it has an f1 which is better than A as well as B, but has a f2 value which is poor than both A and B. In this case, all these 3 solutions are equally good, right. So, they constitute the Pareto solutions and are commonly known as non-dominated solutions. If we have a point over here, let us say this is point D. So, this point D would not be a Pareto point because one of these 3 points A, B, C dominate it, right. So, we would never select a point D if we have points A, B and C. So, in this case, if you see, C has a better f1 value as well as f2 value than the solution D, right. So, D is dominated by C. Here our aim is to find out the set of non-dominated points. So, the syntax of GA multi-objective is given over here, right. So, we need to supply the function handle, the number of decision variables, details about the linear equalities and inequalities, the lower and upper bound, the function handle for nonlinear constraints and options, right. So, if you see, this is similar to what we have discussed for the GA inbuilt function for single objective optimization, and what we can expect from GA multi objective is the decision variable, the fitness function values of the decision variable, exit flag which tells us the reason for termination, output which gives us additional detail about the solution procedure, the final population and its score, right. So, the difference between single objective and multi objective optimization is going to be primarily in terms of this file which we are supplying, right. So, in case of single objective optimization, let us say we have a non-vectorized code. In this case, what we would send is, we would send a 1 cross D vector, right, one solution, right. If we have 3 variables, what we might be sending would be similar to 2, 4, 5, and let us say we have an objective function which is x1 square plus x2 square plus x3 square. So, what the fitness function would return is a scalar value, this one. So, it will do 2 square plus 4 square plus 5 square and it will return that value. So, what we would be getting is 1 cross 1, right. So, this is for single objective optimization. If it is a vectorized code, what we would send is a n cross D and what we would receive is a n cross 1. So, this is what the function file would do in terms of a single objective optimization. In case of multi objective optimization, we have more than one objective, right. So, here this part of the optimization problem you are familiar with, right. Here we have m objective functions, right. So, let us say capital M is equal to 2. So, that means we have 2 objective function, right. In case of multi objective optimization, right. If it is a non-vectorized code, we would be sending a 1 cross D, and what we would be getting back is a 1 cross M. Let us say this is F1 and let us say we have F2 is something else. So, for this 2, 4, 5 we need to calculate the value of F1 as well as the value of F2, right. So, if similarly if there are m objective functions, there would be m such scalar values for this one solution, right. So, this is input to the objective function and this is output from the objective function. If we have a vectorized code, right, so what we would be sending is n cross D, and what we will be getting back from the objective function is n cross M. For each solution we will have m objectives. So, for n solution we will have matrix n cross M which is being returned by the objective function file. Given a solution, our function file should be capable of sending values of both the objectives if we have two objectives, or m values if we have a m objective problem. So, that is the difference in terms of the objective function file which we need to provide, right. With respect to output, right, in single objective optimization, x which is written by the algorithm would be a 1 cross D vector, right, and fval which is returned by the optimization algorithm would be a 1 cross 1 value, right. So, if we have a 3 variable problem, we will get let us say x is equal to 875 and the fitness function value corresponding to this solution would be in fval. So, that is what we will get in terms of output in case of a single objective optimization. In case of a multi-objective optimization, this x may be a p cross D. D is the number of decision variables, right, and p is the number of Pareto points. So, remember we discussed about Pareto points. Depending upon what your problem is and the performance of the algorithm, you may get any number of Pareto points. So, this is F1 and F2. Each of this point on the Pareto front can be realized by a set of decision variables. So, if there are p such points on the Pareto front, right, so we will get x to be a p cross D vector, whereas fval would be a p cross M matrix, right. P because the number of Pareto points is p, and M because the number of objectives are m, right. So, in case of let us say if we have a 5 variable problem and let us say 3 objectives. So, the number of Pareto points cannot be known a priori. So, x would be p cross 5, right, whereas fval would be p cross 3. So, this p is the number of Pareto points determined by the algorithm, right. So, that is the difference between single objective optimization and multi objective optimization with respect to what we provide and what we will get from the algorithm. So, here we have taken an example, right. So, it is a 3 variable problem. The lower and upper bound for all the 3 variables are same, right. So, minus 5 to 5. This is an unconstrained optimization. The 2 objective functions are as given over here, right. This D is the number of decision variables. So, in this case we have taken 3 variables. So, D is equal to 3. Before solving this multi objective optimization problem, we need to first define both the objectives, right. So, here we are creating a function file kur_mo, right. So, it will receive decision variables, right, and we are returning f, right. So, f has 2 values, f of 1, f of 2. So, f of 1 is determined by this expression and f of 2 is determined by this expression, right. So, here we are just measuring the length of x to compute f of 1 and f of 2. So, every time this function is called, it will receive 3 elements, right, and it will send back 2 elements, right. So, it will receive 3 elements because there are 3 decision variable, and it will return 2 values because there are 2 objective functions, right. So, the rest of it is going to be similar to what we have discussed. So, here we define the lower and upper bound, the number of decision variables. We define a variable fitness FCN, which is nothing but a function handle, right. So, we refer to this file kur_mo, and since it refers to a function file, we have this @ operator in front of it, right. And then over here we solve with the default options. So, over here also you can change the options, right. So, you can use options is equal to optim options, right, and the name of the solver, in this case GA multi objective, and whatever options you want to change, you can change that, and you can also pass those options to GA multi objective, right. So, over here, so the output would be x fval. So, fval, remember, it will be a p cross M matrix, or in this case it will be a p cross 2 because there are 2 objectives. We would not a priori know the number of Pareto points, right. So, fval will have 2 columns. So, the first column will contain the value of the first objective, the second column will contain the value of the second objective. So, here we have first objective and the second objective. So, after solving it, we are plotting the first objective on the x axis and the second objective on the y axis, right. So, wherever there is a point, we are putting blue color star, right, and then we are just adding the labels x label, y label. So, this is the plot that we would get, right. So, f1 is in the x axis and f2 is in the y axis. So, for using this GA multi objective, right, so the optimization problem should be in terms of a minimization problem. So, both the objectives need to be minimized, right. So, here this is the Pareto front. If we take any 2 points in this Pareto front and if you analyze, you will see that none of them are inferior to one another. So, for example, if we take this point and let us say this point, right. So, let me call this as B and this as A. So, A has a better F1, right, whereas B has a better F2, right. So, similarly you can analyze all of this. So, remember, as we discussed earlier, the Pareto front need not be convex. So, the problems can have non-convex Pareto front, right. Similarly, it is not necessary that a Pareto front be continuous, right, though it is desired that the Pareto front be continuous. Depending upon the nature of your problem and the performance of the algorithm, you may get a discontinuous Pareto front, right. So, it need not be convex, it need not be continuous. So, here we did not have constraints. So, if you have constraints, right, and if the constraints are conflicting, then there will not even be a single feasible solution. So, if there is not a single feasible solution itself, then there will not be any Pareto point also, because the Pareto points need to be feasible, right. So, you can have a case wherein the number of Pareto points is 0. So, for example, problems which do not have any feasible solution, you can have a Pareto front in which the number of point is only 1. So, a trivial example is wherein the number of feasible solution itself is 1, right, and a common misconception is that if you have 2 objectives, you will get only 2 Pareto points. So, that is also not true. The other algorithm that MATLAB has for solving multi-objective problems is Pareto search, right. So, its use is similar to GA multi OBJ, right. So, here the name of the function is Pareto search, right. The input is identical to GA multi objective. Output, these 4 values are identical to GA multi objective. In GA multi OBJ, in addition to this 4, what we got was the final population and their scores. So, scores are nothing but the objective function values. Over here we will get residuals. So, this residuals is a structure, right. So, here we chose to give a name residuals, you can give any variable name. So, it would be a structure and it will contain the constraint values at the solution points x. The dimension of x would be p cross d, where p is the number of Pareto points and d is the number of decision variables in your optimization problem. Fval would be p cross m, right, where p is the number of Pareto points and m is the number of objectives that our problem has. So, the solution procedure is also same. This is the same function file which we explained earlier. So, this part of the code should also be clear to you. It is exactly the same which we discussed. Here we call the Pareto search function and supply the necessary inputs. So, there are no constraints, right. So, we give empty brackets. We have lower and upper bound of -5 and 5. So, that is given over here, right, and similar to last time we also plot the Pareto points. So, this is the same problem. If you recollect the previous figure and look at this figure, you can see that they are not identical, right. So, the performance of Pareto search and the performance of GA multi OBJ would be different. Just like for single objective optimization, GA multi OBJ is also a stochastic technique which is based on genetic algorithm, right. So, it has to be run multiple times. So, every time we run it, we may get a different Pareto front. So, let us say if we run for 10 times, we will get 10 Pareto fronts, right. So, all of these 10 Pareto fronts can be combined and we can identify the points which are actually non-dominated. So, for every time we solve, we will get a set of non-dominated points. When all these points are clubbed, all of them need not be non-dominated, right, because we are combining the results of different runs. So, all the points can be combined and a non-dominated sorting can be done. So there are inbuilt functions in MATLAB which can help you do non-dominated sorting, and that is how you can get the final Pareto friend from different number of runs, right. So similar to statistical analysis that we did for single objective optimization, we can also do statistical analysis for multi-objective optimization. However, for doing statistical analysis for multi-objective optimization, we need additional measures, right, that you can look into standard multi-objective optimization textbooks. We will not be discussing that over here because the scope of our course is primarily single objective optimization. Since MATLAB has inbuilt functions to solve multi-objective optimization problems, we just discussed how to use those functions to solve multi-objective optimization problems. Now we will look into the implementation of multi-objective optimization. So this is the script file which we have written over here, right. So we are clearing the command window, the workspace, and closing all the figure files if they are open. We are defining the upper and lower bound in line 3 and 4, and then in line 5 we are just determining the number of variables. In line 7 we are assigning KUR_MO, right. So that is the objective function file which we have written for this problem, right. So that we are assigning to fitness function, right. So this fitness FCN is a function handle. So now let us look into this fitness function file. So KUR_MO. Right. So here we receive the decision variables and we pass the objective function values, right. So these are the two objective functions which we had seen earlier. We calculate f of 1 and we calculate f of 2. So to calculate f of 1 and f of 2, we need the value of this d as to how many decision variables are there. So that is why we determine the length of x, right. So every time the length of x is determined and f of 1 and f of 2 are calculated, and it is returned back to genetic algorithm in this case. Here we are using GA multi OBJ to solve the problem, right. So this is the name of the inbuilt function, GA multi OBJ. We are providing the problem that is to be solved, right. We are supplying this name fitness FCN. So the number of variable in this case is 3, right. So that we have calculated here. Here we do not have linear inequalities or linear equalities, so we have given empty brackets, the lower and upper bound, and we do not have any nonlinear constraints, right. So we have given empty bracket. So this is not even required. So as we discussed, the size of this x is going to be p cross d, where p is the number of Pareto points which we do not know a priori. Only after the solution we would know what is the number of Pareto points. Fval in this case will be p cross 2 because there are two objective functions, right. Since we have two objective functions, right, so here we plot that, right. So fval of all rows first column, comma fval of all rows second column, right. So basically we are plotting f1 and f2. So wherever we have a data point, we want to mark it with a blue color star, right, and this is just adding the x label and y label. So now if we execute this, so we get this Pareto front. So this is the Pareto front which we had shown you earlier, right. So it's fairly simple to solve multi-objective optimization using this function, right. So here if we look at the variables, so over here fval, if we see, it is 18 cross 2 and x is 18 cross 3. In this case it has determined 18 Pareto points, and since there are 18 Pareto points and the number of decision variable is 3, we get 18 cross 3 for x, right. So these are the decision variables. So the fitness function corresponding to each of this solution is in fval, right. So this is the fitness function. So for the first solution, which is minus 1.1552, minus 1.1539, minus 1.1541. The first objective function value is minus 14.442. The second one is minus 11.62. Similarly, we can interpret the rest of the solutions and their objective function. So again, since this is a stochastic technique, we need to fix the random number generator to be the twistor algorithm, and let us say the seed is 1. So now if we execute, let us see how many points we get, right. Okay, so we get 18 points. Now what we are ideally supposed to do is, we are supposed to run it multiple times, right. Again we need to put a for loop over here and run it 10 times, and every time change the seed and see what is the Pareto front. So let us say with a seed of 10, how many Pareto points do we get? So even in this case we have got 18 Pareto points, right. So it is not necessary that we get the same number of Pareto points every time. As we had discussed for single objective optimization, right. For multi-objective optimization also we can use this optim options, right. So let me uncomment this, right. So what we are going to do now is, we are going to use the output function feature of MATLAB, right, for solving optimization problems with respect to this function GA multi obj, right. So, optim options, the name of the solver, the keyword, and this is a function file that we have written. So, we want MATLAB to do something at the end of every iteration. So, what we want to now see is the Pareto front being developed, like for at the end of every iteration we want to see what is the Pareto front, right. So, since we want to do that, we can implement it using the output function feature of MATLAB. We are using this variable name options and using this inbuilt function optim options to make sure that GA multi objective after every iteration executes what is given in this function file, right. So, here since we do not have a nonlinear constraints, we need to put empty bracket, right, and remember GA multi objective does not support integer variables. So, we do not need to give empty bracket, right. So, over here we can give directly option. So, now when MATLAB solves it, it will take these options which are defined over here, right, and here now let us look into this function file. So, similar to single objective optimization, in multi objective optimization also, when this function is being accessed by GA multi objective, it supplies options, state and flag, right. So, if we change the options in this file, we need to return flag as true, right. So, in this case we are not going to change the flag. So, we are just saying opt change is equal to false, and as opt change is passed back to GA multi objective. So, this state contains information about solutions. The objective function values can be accessed by state dot score. So, what we are doing is we are accessing state dot score and we are saving it in another variable current score, right. So, it will have two columns, state dot score will have two columns and as many rows as the number of Pareto points discovered at the end of that particular iteration, right. So, just like we plotted previously, here also we plot of current score of the first column and current score of the second column. So, what we are doing is just plotting both the objective functions. Here we are plotting it with red color, right, and since this dot has a very small size, we are increasing the marker size to 12 and then we are asking MATLAB to immediately plot it, right, so that we can see the Pareto front actually moving as the iterations proceed. Similar to last time, let us just put a breakpoint over here and execute this file. So, if we look at state, right, so this is 0th generation, right, and it has this score, right. So, score is the objective function values. So, this is the population, there are 50 members and for each of the member we have two values for objective function, that is why this score is 50 cross 2. So, we can access score by just writing state dot score. So, state is a structure and score is a field in that structure, right. So, state dot score gives us all the values, it is just these values which we are plotting. So, minus 14.6459 in the x axis and y axis 4.1618. So, that is the point we are plotting, right. So, similarly we will plot all these 50 points. So, now let me just remove this breakpoint and provide continue, right. So, here if you see the Pareto points are moving, right. So, this is not the decision variable space, this is the objective function space. This is at the end of all the iterations, right. So, the blue color points indicate the final Pareto front, whereas the red color dots are solutions which are dominated. Since we work with a population size of 50, which is the default population size for GA multi objective, we will have 50 points, right. So, all these points are dominated, right. So, the red color points are inferior points, whereas the blue color points are the trade off solutions, right, and they constitute the non-dominated points or the Pareto points. That is how we can solve multi-objective optimization problems using MATLAB, right. So, again all the features which we discussed for single objective optimization can be employed for multi-objective optimization also. With that, we will be concluding our discussion on inbuilt optimization functions which are available in MATLAB. Right. So, as part of this we had seen function linproc to solve linear programming problem, int linproc to solve MILP problems. We had looked into fmin UNC and fmin search, right. So, it was used to solve unconstrained nonlinear programming problems. Remember, it does not support bounds on decision variables, right. So, for only bound constrained NLP problems, like there are no linear or nonlinear constraints, in that case we had discussed simulated annealing and particle swarm optimization. The inbuilt function of MATLAB, particle swarm, does not explicitly support handling of the constraint, but As discussed in the earlier lectures, you can use a penalty approach to incorporate the constraints in the objective function and come up with a fitness function, right. And for constrained nonlinear programming problems, we had looked into fmincon, pattern search and GA. For MINLP problems, again remember, only if there are no equality constraints, right. So, if there is an MINLP problem with equality constraint, we cannot use GA, but if we have MINLP problems which has only inequality constraints, linear as well as non-linear, we can use GA to solve MINLP problems. We also looked into this 4 features available in MATLAB with respect to optimization solvers, right. So, we looked how to override the default options. We also discussed on how to have a output function, right. So, the output function is called at the end of every iteration, right. So, if you want to modify something at the end of every iteration, we can write it in a function file and use this output function feature of MATLAB. We also discussed on vectorization and parallel computing. Finally, we looked into these 2 functions of MATLAB which can be used to solve multi-objective optimization problems. These functions can be used only for minimization problems. So, if we have a maximization problem, we need to convert it into a minimization problem and then use the appropriate function. With that, we will conclude our discussion on MATLAB inbuilt solvers. We will now move on to 2 other software, GAMS and IBM iLog Simplex Optimization Studio. Thank you.